Hi everyone. So welcome to the 20 lectures in 20 minute series. I am Mahesh and I'm going to be talking about bird's eye view of AI today. A lot of buzzwords recently. I've all heard of big data, machine learning, deep learning, and AI. And how these words have trended a lot over the last few years. In the last 5-6 years, you see that they're almost competing with each other in terms of the world. Today, I'll be talking to you about these buzzwords, what they mean, and some of the applications. Who am I? I'm Mahesh Kalavai. I've been in the data science and engineering. Currently, the chief data and analytics officer for TVS Motor and Group companies. I've been in the space across several industries prior to joining TVS. I was with banking and consumer retail. And so I've had a very good idea of how these technologies have evolved over time. Though I do not know much about medicine, except the fact that my father is a doctor, he's retired now, and I grew up in a small town in India, right next to his clinic. So I've seen my father both as a doctor and also an entrepreneur in the medical field. And a lot of what I have tried is to talk about applications from that little knowledge that I have. In the presentation today, we'll be talking about how data and analytics are used for generating insights, for foresight, prediction, for computer vision, and lastly, how they all build up to AI. Let's start with your field first. How does sight work? We see an image, essentially light rays travel from an object, they hit our eye focuses them, and we get an inverted image under retina. This is then carried by optical nerves to the brain, which somehow deciphers this to be an object like the tree. How does the brain do that? Right? So we call that an algorithm. So the brain has an algorithm which is really a repository of previously seen images. So that's a simple algorithm that the brain uses. Slightly different example is foresight, prediction. So now here is a tennis match. This is a match between Roger Federer and David Ferrer. And you see that Roger Federer is attempting a drop shot. Even as he attempts the drop shot, you see the opponent running. And a few seconds later, the opponent Ferrer is able to reach the ball. So how does our eye, right, that sees a shot and is able to predict where the ball will be a few seconds later? Similar process, we see the ball, the optical nerves carry that information to the brain, and this time the brain does a prediction algorithm in using the repository of previous such shots that the player has seen. That, in a nutshell, is how data analytics works. Well, let's take a look at it from a different angle. What we saw today is how a brain uses information when we see. What we did not talk about is the tons and tons of balls that tennis players hit to train themselves, to train their brain as to where the ball will be, to develop a prediction algorithm for the ball. That once you train, then during a match, when they see a ball, their brain automatically picks up where the ball will be, right? So that is we see. Another thing that happens is every such instance, a reinforcement happens. If their prediction is right, it reinforces that the algorithm works right. Or if the prediction is wrong, it tells the brain that they need to go and get some more. That's how our brain operates. And ultimately, data analytics is such a field like that, right? On the left side, and where you see tennis balls, is essentially the equivalent of tennis balls, the data that feed to our computer and to develop prediction algorithms. Now, what from not a medical man, but from what I understand, we don't quite understand how our brain operates just yet. But computer algorithms are more simplistic, right? So they understand mathematics. So a lot of the prediction algorithms that we have mathematical in nature. So on the top, you see here are simple charts, the ones that we've seen in school. And essentially, if you want to detect if somebody has, let's say, eye power, and let's assume the only thing that matters is somebody's age. In which case, because it's just one parameter, you can develop an easy to interpret mathematical relationship. But let's assume that the power of the eye is not dependent on one factor, namely age, but two factors, namely age and gender. With just the addition of one more factor, one more feature, you see how complex the graphs become. In reality, for us to develop good prediction algorithms, we typically use about 20, 25 different attributes or features, and therefore you can imagine the set of complexity that goes behind it. Now, such a mathematical relationship can be derived using one of two ways. On the left side is what we call as an expert system. This is somebody like a tennis coach that comes and tells you where exactly you need to run whenever you see a drop shot. Or the equivalent of that, let's say in the case of science, is a teacher theoretically talking to us about E equals mc squared. Does it work? It works, right? But what it does not do, it does not learn very well over time because you need an expert every time. On the right side is typically how tennis players train, right? So they train a lot, they understand how balls move as a result of these training, as a result of these data samples they see through their training. Or in a physics example, this is how we develop data and understanding through experimentation. So the first on the left side is called expert systems. The one on the right, essentially letting data intuitively tell us how things work, is called machine learning. That hopefully gives you a good understanding of machine learning. Now let's see the application of machine learning in the so forget the supervised and unsupervised algorithms right now. So let's say these are actually actual examples that they pulled up from the net. The first one is detection of something like glaucoma. 75 pictures were taken, some with normalized, some with eyes with glaucoma, and an algorithm called support vector machine was used to determine the algorithm on how do you detect somebody with glaucoma. Same thing was done with using a different set of techniques, but ultimately to see the severity of keratoconus, right? So this is about detecting situations that exist using data. Same thing can be employed to detect or predict rather, which is foresight. Again, 31 patients records, 9 demographic information, 17 other factors were taken to predict if somebody had a cataract. So of course, all the three examples we talked about are presence or absence of a particular medical condition, but you can do the same thing in a related field. For example, let's say in your eyeglass store, there is somebody who has come and bought spectacles. You can determine based on something like association rules on whether this customer is also somebody who can buy a lens cleaner. So these are some of the examples of how machine learning can be used. Now let's go to the next topic, but let's go back to the same example of how vision works. In a different picture, same idea like the tree. This time, this gentleman is looking at a coffee cup. Both eyes see the image. This is transparent, and in the visual cortex, we understand there is a color. Now, how does this perception happen, right? So, color, right? I see the dark and light pixels, 3 different cones, activate 3 different primary colors, and they are taken to our brain. And in the brain, from what I understand, there is a place called a section of the brain called V1, where these visual signals are broken down to detect edges. And such edges are then brought to a place called V2, where these edges are combined to create an image like this, to create boundaries, to understand texture. And then several other such transformations later, voila, we are able to see the object as a teddy bear. That's how human brains work. We also know that computer can also see now, and we call that computer vision. Of course, we all have cell phones which does that now. And in the picture, what you see here is a detection where you see from the camera and you're able to identify people from. The methodology of developing the algorithm is similar to what we've seen in the past. A set of images are fed, which helps the computer develop an algorithm, and ultimately using that algorithm in step 2, when you feed new pictures, you get to understand what the picture is. Now, if you look at how such an algorithm is developed, it is not very different from how we think our eye works. complex picture. I'm going to start at the bottom of the picture. Let's say you feed an object like a hair, it's broken into multiple pixels, colors, and then the first layer, the first stage detects the edges. These edges are brought together to determine parts, and finally the parts are transformed. Very similar to how we think our brain operates, and that's what no wonder this technique is called neural networks. Above is a more complex interpretation of the same. This is the actual architecture. This is how the programming is done in the computer. And you can see several layers here, right? So, and we call such a network a deep network if you see multiple such layers. And this is an example of a technique called deep convolutional neural network. This is essentially how we look at object detection using computer vision. So this is deep learning, right? So the advantage of deep learning over traditional machine learning, which is the previous set of topics we discussed, is with more data, you get better performance. So as the world has gotten more and more data, we have seen that deep learning has become employed. So today, when it comes to computer vision, comes to voice recognition, text, you find a lot of application of the chart at the bottom right is an example of how the progression has happened. This is a popular competition called ImageNet Challenge, and where a set of images are thrown and one has to identify, or we have to develop algorithms to identify the pictures. This chart measures error rate. So the lower the bar, the better the algorithm is. So humans, right, according to this chart, have performed at about 5% error rate or 95% accurate. And you see, after having employed deep learning, our computer algorithms have gotten better, significantly better over time, and have now started regularly beating human level of detection of computer images. That's the progress that has been made in a field like computer vision. Several applications, of course, all of us work with computer vision today. We can understand activity, we can understand attire, we can use it for gaming, can create arts. The top one is actually an art created by a computer algorithm works or can in 2018. And the bottom is actually a picture of our dog. And because the neural networks use layers, you can apply any layers, and that's what we call. All of them ultimately use the same underlying neural networks. So this is an example of deep learning. Now, this also has applications in the healthcare domain. Right? At the top is diabetic retinopathy. This is actually a famous example, contributions of Shankara, of course, along with Arvind and Narayana Nethralaya with Google a few years ago, where a set of folks were able to identify healthy versus people that have diabetes. Developed. Computer vision is a very ripe and rich field of healthcare because a lot of medical data is visual in nature. And at the bottom, you talk is an example of an article from a magazine called Starters Insights, where they looked at 270 startups that are using computer vision in one way, shape, or form. And the five were deemed as winners, five different examples from heart to gastroenterology to surgery to lungs to oncology. So you can see the widespread application of something like deep learning. Let's move on to the third topic, right? And we can start with data. So over time, we have seen an explosion of data. And it is largely, we see the explosion of data largely like, and you see that we project over the next 5 years, we will double the data that we have generated over the last 10 years. This is the extent of data. And on the right, you see a manifestation of it, right? So if you log on to Amazon or Netflix or LinkedIn, you find that the content is tailored for you, personalized for you. So these things go hand in hand, and we'll see how in the next slide. So on the left is big data. So as more data gets produced, the cost of storing it and processing it is also getting cheaper. Environments such as cloud environments get stood up, and where we can do pay per use. Because there is a lot of information, as consumers, we also crave for personalization because there's too much to consume. So the need for personalization is high on the one hand. The ability to personalize is also higher because of the richness of data. And in a lot of industries, this creates a big differentiator for one company versus another, the ability to differentiate through personalization. This has application in the field of bioinformatics as well, right? It takes about 200 gigabytes. And by 2025, we expect about 100 million humans to have this genome sequencing. Cost of a genome sequence is rapidly falling, more than typically a Moore's law, which is used in computing. And with such available data, we have to use a lot of the big data technologies like cloud, plus we also have to divine pieces of information, right, from a very large data. From data paucity, we've come to an era where there is so much data that you need to be really diligent in picking up the differences of the signals. And that is essentially the employment of big data. The benefits are, of course, very huge if you're able to do that. Personalization, typically in the industry that I've worked with, we call it personalization. The medicine field is called precision medicine. We apply to personalized medicine. The same idea can be replicated when it comes to caregiving, wellness, pricing, etc. So you can imagine a world in future where the medical facility, the caregiving is as personalized as one watches a Netflix channel today. So that is possible with the big data. Lastly, of course, we started with AI and we're just getting into the idea of AI towards the end of the talk. What is artificial intelligence? Artificial intelligence is a broad concept which talks about how can we get computers essentially to think like human, like natural intelligence. It has algorithms like machine learning or expert systems. It also has a few other pieces that have got nothing to do with that. Talk about some of them. A class of algorithms are called machine learning. A subset of that, where you have a lots of data and more complex phenomena, is called deep learning. And ultimately, the technologies that create a lot of this is possible by using and processing data, well, is called big data. So hopefully that gives you a bird's eye view of what AI is. Now, we talked about a few pieces beyond algorithms that are important. Touching upon a few here. Because the technology used in AI today is machine learning or deep learning, meaning not expert systems. We rather learn from data. The data, if the data has unfairness of any kind, based on how we do our business today, how we make decisions today, that is essentially what the. As an example, in the field of medicine, medical trials, if a particular segment of the population is underrepresented or unrepresented, then that is what the computer's algorithm is going to learn. So it creates biases and one needs to be watchful for that. Another important piece that is coming up is awareness, consciousness about data and privacy. And India also has a few bills that are noted here. And that becomes very, very important as more data becomes available and the consciousness of our data goes up. Ethics is another important piece. It again brings human issues to the fore. For example, very recently, unfortunately, some countries have had to make choices of which patients get hospital admissions and which ones do not because of scarcity. Such decisions, where unfortunate, do happen. We make them as humans. But when a computer is given the power to make it, though the same decisions are made, somehow it feels more colder, right? More inhuman. And these are important issues for us to think through as we look at AI applications. Lastly, business models, again, with a lot of data, if you look at fields like fields with network effect like Uber, ride sharing as an industry, the more people join a particular network, the more power the data brings. So such could also become a reality in the field of healthcare. A lot about artificial intelligence. Towards the end of the topic, I want to talk a little bit about natural intelligence. While this has been phenomenal, not even close to where, not close to where our brain is. Brain, for example, has 86 billion neurons, and about 6 years ago, 83,000 processors to simulate 1 second of a brain. Not only is the brain so powerful, it's also supremely efficient. We do all of this with very little power. And today's computers require 500,000 times the same power for a similar activity of our brain. So such is the power of our evolution, of our natural intelligence. So we've got some ways to go in AI. That's it. There are several applications. In today's conversation, we talked a lot about diagnosis, medicine side. Same thing is true for other accesses, right? Like access to people that are remote. How do we make, how can this be used for managing hospitals and particularly precious assets like through patient flow optimization or outpatient management for follow-ups and the like. The applications are a lot. A lot of you will be putting them into good use in the years to come. Towards the end, we will not have time to cover this. I wanted this to be in the video. Technology predictions are linear in nature, so a lot of innovations act with each other to create immense possibilities in the future. So what happens is we tend to over predict technology's reach in the short term, but under predict. I will leave this in the video for future consumption. Otherwise, it has been wonderful to talk to you a little bit about the applications of AI. Thank you so much.